So with this group, this next kind of section of our class, we're going to deal with objects that have constant acceleration. So that means they're speeding up at a constant rate, they're slowing down at a constant rate, one or the other, okay? We might see instances where an object speeds up, then stays constant for a while, right? No acceleration, then they slow down, then they move backwards, they move forwards. When we have situations like that, we'll break them up so that we're dealing with a portion of time in which the object is accelerating at a constant rate. Okay, so we don't deal with things that speed up and slow down in the same equation. Okay, we deal with basically one instance or the other. Does that make sense? We break it up into portions of time or portions of the path that have uniform acceleration or constant acceleration. Okay, so these are, I'm going to give you basically 3, maybe 4 commonly used equations called your kinematic equations. Okay, these are called the kinematic equations for constant acceleration. Okay, but I will just call them your kinematics equations. These 3, 4-ish, okay, the fourth one's not used very often. These 3 equations are used basically from here until the last day of this class. Okay, we use them all the time. For lots of different situations. We're going to start to manipulate them when we deal with rotational motion. We can make them go in the x direction or the y direction. They are really, really, really useful. So we'll see these equations a lot, just maybe in a couple different forms. Okay? None of these equations are valid unless we have stipulated that the acceleration for that portion of time is constant. Okay, so it might be speeding up at 3 meters per second squared, might be slowing down at 3 meters per second squared. Either of those things is fine as long as we understand that it's constantly accelerating or decelerating. Okay. What did we say last class about a negative acceleration? What's negative acceleration tell us? Does it always mean that it's slowing down? It could be the opposite of velocity if it's slowing down. Negative tells us the direction of the acceleration. Okay? So it doesn't always mean that it's slowing down. It means that it's the direction of our acceleration. So just kind of take that into account. It does not always mean that it's slowing down. So don't try to keep that rule. Okay? Here is our first kinematics equation. Okay, first kinematics equation. And if you want to wait until we get all of them to put them on your equation sheet, that's fine. If you want to do them as we go, that's fine also. It really doesn't matter. But we're going to walk through what these variables mean. And we talked about them a little bit briefly last class when we introduced acceleration. But we're going to go through them again. Okay? We said v sub 0 is equal to initial velocity. Okay? And these are the variables that your book uses. Okay, the other physics textbook uses v sub I for initial. Okay, but we're going to stick with what your book uses so that it's consistent. So the 0 means when time is at 0, right? When we're looking at our initial position, our initial velocity, initial time, that's what speed we're moving. Just v by itself is going to be equal to what? Yeah, final velocity. Okay, and tell me the units for both of these velocity variables. What's the most commonly used unit for velocity? Meters per second. Good. Meters per second. All right, we have to be able to pick out variables based on their units. That's going to make reading those word problems a lot easier. Okay, pick them out based on the units. What do we know that A stands for? A is equal to acceleration. And what's the units for acceleration? Very good. Meters per second squared, or you might see it as meters per second, or it could be kilometers per hour squared. Okay, any of those units could be acceleration units, but it's distance per time per time. Okay, it's the rate at which our velocity is changing. All right, and then what do we know about little t? T is time, and that's given in what unit? seconds. Okay, so things that are specific about these kinematics equations is that our units have to be consistent across the board. So if my velocity units were both in kilometers per hour, I would want my acceleration units to be in what? Kilometers per hour squared. And what would I want my time unit to be in? Hours. Okay, so you have to make sure that you've got consistent units across the whole board. Okay, if your acceleration is given in meters per second squared and your time is given in seconds, we might want to convert our velocity to meters per second, okay, because we have a shortcut to do that. Just understand that you have got to have consistent units because someone will forget to do that, okay, or multiple of you will forget to do that. Just keep that in mind. Second kinematic equation. We'll get down to this bottom text here in a second, but just go ahead and get that equation down. So let's talk through kind of what these variables might mean. What do we think X stands for? Position, good, or displacement, good. Okay, we'll go ahead and call X displacement. And is it going to be initial displacement or final displacement, do you think? Yeah, good. This is final. Okay, because it's just X, which means X sub 0 would be initial displacement. Okay, and if we see this text out at the bottom, it says most of the time X sub 0 can be set to equal 0 since it's a starting location, right? Displacement in and of itself is telling us how far from our starting position we are when we end up somewhere, right? So if we have an initial displacement, that's asking us how far are we starting from our starting point. Okay, most of the time it's going to be 0. Okay, because we get to choose the origin. We talked about that a little bit last class. We get to choose the origin at our starting point. Okay, so most of the time, X sub 0 is going to be equal to 0. And we'll see that as we go through a couple problems here. All right. We know what V sub O means, which is initial velocity. What's T? Time. What's A? Acceleration, good. And then it's important to understand here that only the time is squared in this term, okay? You do not square that whole 1/2 AT, you just square time, okay? So it's T squared there at the end. That's really, really important, okay? Just T needs to be squared. All right? Questions there? All right, good. Let's look at our last really commonly used kinematics equation, and then I'll give you one more that's a little bit less common. But this is the third of our big 3, and then we'll get one more. Okay, is there anything in this equation that we are unfamiliar with? V is final velocity. V sub O is what? Initial velocity, good. Acceleration. And then what is this really look like here? If we were going to write this term a different way, what would it look like? Final displacement minus initial. Yeah, it would look like delta x. Okay, so sometimes in your book or your other equations you might see it written like that. V squared equals V sub O squared plus 2a delta x. Okay, it means the same thing. Final minus initial. Okay, and most of the time if initial is 0, right, you're not subtracting from anything, so it's going to make your term a lot easier and make solving for that a lot easier. Okay? Questions there? All right, we got our big 3 kinematics equation. Here's one more that's a little bit less commonly used, but it is used occasionally. Okay? This is to solve for pure average velocity. Okay? Pure average velocity. So if something has the bar over that variable, that just means average. So all we're doing is taking final plus initial divided by 2. That's it. Okay, this is the least commonly used of our 4 equations. But this is just to find a true average. The first thing that's really important with these physics word problems is that you don't assume what you think they're going to ask. Okay, you have to read the whole problem. I know that seems like common sense, but a lot of people will try to just assume like, oh, I've seen a problem kind of like this before, this is what they asked, blah, blah, blah. And then you waste time solving an equation that you don't need. Okay, so just make sure that you pay attention to see what they're asking for, because the problem could be a lot simpler than what you're making it. Okay, draw a diagram if necessary. This is necessary a lot of the time, right? We saw a couple classes ago, our diagrams can be really, really simplistic. Okay, let's say I'm on top of a cliff and I want to toss a ball off the cliff. Okay, blah, blah, blah. That's all that needs to happen. Okay, that's my diagram. But it's showing me that this object's going up and then going down. Okay, and that's it. That's my diagram. But I can see what's happening in the motion a little bit better. Okay, let's say that I kick a football. So here's the ground, here's my origin. Football's going to go up, but then it's going to come back down. Okay, so I can see here that it reaches its peak height. I can see what's happening, that it's a symmetrical type of motion. Those types of things give me good clues while I'm trying to solve that physics problem. Okay, so we can make things really simplistic, and then we'll start to get into the diagrams a little bit more in depth as we move through it. Okay? Write what you know and determine what's to be found. Okay, that's where we start making our list in the margins. So right now we just saw that we've got final initial velocity, final initial displacement, acceleration, and time. That's already, 7 variables. Okay, so if we're dealing with 7 variables, we can't just start plugging in numbers, right? You've got to keep yourself organized. 7 variables is almost the minimum that we're going to deal with. We'll get into problems where we've got 10 to 12 different variables that we're looking at in terms of horizontal and vertical velocity, horizontal and vertical displacement, all that kind of stuff. Okay, so you just need to really make sure that you're paying attention there. Oops, still on my drawing tool. Consider what equation we should use. If we have an equation that we need to solve for acceleration, or if we need to solve for time, I want you to take a look over your 3 kinematics equations here. Okay? Let's say that I need to solve for time, but I don't have a final velocity that's been given to me. What kinematics equation could I use? The second one, right? Because final velocity is not even in that equation, and it has time. Okay, what if it's the opposite of that? What if I'm not given a time, but I want to solve for final velocity? What equation could I use? The third. Okay, so there's lots of different situations that are going to kind of really determine, right? It's going to stipulate what equation you can and cannot use. You can always take 2 steps and kind of get to any equation you want, but there's an equation that will work for every problem, usually in 1 step, usually. Okay. Calculate, then check to make sure our answer is reasonable and does it have the correct units. Okay. Most of the time, we can get reasonable answers in high school physics. Okay, sometimes when I make up problems, the answers get a little scary. Okay, a little unrealistic. I'll just be honest with you there. But I try to have answers that are semi-realistic. Okay, so just, if you think a number is out of this world, maybe you're right, maybe you're not. Okay. All right, let's try a few practice here. Okay, so I'll give you a second to get this written down, and then we're going to talk through this one together. First of all, are we going to solve here for final velocity? Or are we given a final velocity? Or what variable do you think that we're solving for here? Okay, we're given a velocity here that says it has to reach that speed before it's going to be able to take off. Okay? It gives us the length of the runway, and it gives us the acceleration. So let's kind of just start writing down what we know here. We know the plane accelerates at 2 meters per second squared. We know the final displacement is 150 meters. What do we know about the initial displacement? Good, it's 0, because that's our starting point. That's where the plane is starting from. Okay, so it's 0. It asks us, can this airplane reach the proper speed to take off? So we know this is the speed that it needs to reach. So are we going to plug that into our equation, or are we going to use it to compare? We're going to use it to compare, which means we need to solve for what variable? We need to solve for final velocity. Okay, and what do we know about our initial velocity? It's 0. Okay, because when we say a plane takes off, we mean to leave the ground. Okay, so we're looking at this section of our motion where the plane is going from 0 to right before it leaves the ground, right? So we're looking at the time that this plane is on the runway. Does that make sense? It's going to start from a stop, and it's going to start accelerating until it reaches that end of that runway where it needs to go wheels up. Okay? Any questions about where we got these variables from? All right, now let's start plugging into our kinematics equation. Which kinematic equation should we use? The third one, the one that looks like this, right? V squared equals V sub O squared plus 2a x minus x sub 0. Yeah? All right, we said we are solving for final velocity, so that's going to stay right there. 0 squared plus 2, 150 minus 0. To get v by itself there, what do we need to do algebraically? Good, we're going to square root both sides. So that means our velocity that our plane is going to reach at the end of the runway is equal to what? 24.5 meters per second. Do we agree with that number? So, is our plane going to be able to take off? No, they're not going to reach the proper speed. Okay, so that problem, right off the bat, you probably think we're going to plug in 27.8 meters per second as final velocity. Was that the case? No, it wasn't the case. That didn't work like that. So that's an example that you have to read the whole problem. Think about the big picture and what we should be solving for, and then really go back to evaluate those variables. Okay? So no, it's not going to reach its proper speed. Do we all agree there? Very good. Okay? We talked through all that. Okay. What length does the runway need to be in order for the plane to have a successful takeoff? So now, what are we going to use for our final velocity? We're going to use that 27.8 that it's got to reach, right? So, but what variable are we not going to use this time? Yeah, we're going to solve for x instead of using that 150, right? So here we're going to use the velocity from the last problem, which they told us it needs to reach 27.8. Okay, so that's going to be our final velocity this time, because that's the speed that it has to get to. Okay, we know initial velocity is 0. We know our acceleration is going to remain the same. We know our initial position is 0. We're going to solve for what length does that runway need to be in order for it to get up to the right speed. Okay, are we on the same page here? Okay. Can we use the same equation that we used in the first problem? Yeah. Okay, we can use that same equation, which was v squared equals v sub o squared plus 2a x minus x sub o. Now we're going to plug those numbers in. So 27.8 squared Okay, so 27.8 squared is equal to 772.84. Equals 4x. To get x by itself, what do I need to do? Divide by 4. Which means my final displacement of my plane to get up to the correct speed is 193.21 meters. We agree? So our runway is 43.2 meters too short. Okay, it's not long enough for the plane to really reach that correct speed. So that means that's the distance or the displacement that that plane needs to travel in order to fix that problem. What might be another way that the plane could fix that problem? Having a bigger acceleration. If it could accelerate at a faster rate, that would help too, right? We could maybe use that shorter runway. All right, let's go ahead and try this one on your own, please. Car starts from rest and accelerates uniformly for 8.4 seconds, distance of 230 meters. Find the acceleration. So we ended up to come out at 6.50 meters per second squared. Okay, let's try this one. It tells us it accelerates from 20.5 to 52.1. Find the acceleration, then find the distance traveled. So this is just two parts. Okay, you have to have the acceleration first. The one common theme through all of those kinematics equations is you have to have acceleration. Acceleration is in every one of those equations. Okay, so you have to have that. So is initial velocity, but whatever. Okay, acceleration is something that you have to have in every single one. Okay, initial velocity is a lot of the time 0. Acceleration is not, so you have to have acceleration for all of those. Okay, so let's go ahead and try this one.
Bless you. Oh, I didn't do it. I did the harder way.
Okay, so solving for acceleration here mathematically, what's my first step? Subtract this over. That's big. Some of you will try to divide that over. Okay, so 52.1 minus 20.5. 31.6 equals 4.18 times A. We divide 4.18 over, which means our acceleration is equal to 7.56 meters per second squared. So this shows that using either kinematics equation here to solve for displacement will work. Okay, they are off by a very, very small margin. Okay, that rounding is not a problem. Okay, so using either kinematics equation there works. You get a consistent acceleration. Okay, and that could even be with using, keeping the acceleration in your calculator or keeping numbers in your calculator. Those could be little rounding errors.